In June of 2024, a Chinese spacecraft scooped up a handful of grey dust from a crater on the far side of the moon. Nobody had ever done that before. Not the Americans, not the Soviets, not anyone. Every gram of moon rock ever studied on Earth, from the Apollo missions to the Soviet lunar landers to China's own earlier Chang'e 5 flight, had come from the near side, the face that has stared at us since before there were eyes to look up. The far side stayed a mystery, mapped from orbit but never touched. Chang'e 6 touched it. The lander came down inside the Apollo Basin, a crater within a crater, sitting on the northeastern edge of something called the South Pole-Aitken Basin, the oldest and deepest impact scar on the moon. It drilled and scooped for about 2 days, sealed 135.3 grams of far-side material into a capsule, sent that capsule up into lunar orbit to dock with a waiting orbiter, and rode it home. Total mission length, launch to landing back on Earth, 53 days. The spacecraft had launched on May 3rd, 2024 from the Wenchang Space Launch Site, and by June 25th, the return capsule was already back on Chinese soil in Inner Mongolia, samples intact. When the samples reached Chinese laboratories, scientists started dating fragments of basalt, the dark volcanic rock that fills lunar lowlands, using the radioactive decay of lead isotopes locked inside tiny mineral grains. Most of what they found lined up with expectations. Then 107 fragments came back with almost exactly the same number, 2,807 million years old, give or take 3 million. That number should not exist, or at least not the way it arrived. Basalt that young means lava was reaching the surface of the moon 2.8 billion years ago, long after a body as small as the moon should have lost enough of its internal heat that magma stopped forming. And when researchers checked the chemistry of those particular rocks for the radioactive elements that generate the heat needed to keep magma flowing, potassium, thorium, and a handful of rare earth elements, they found almost none of them. A billion-year-old lava flow, with barely any obvious fuel source to explain it. That contradiction, sitting quietly in a handful of far-side dust, is where this story starts. For decades, the moon's two faces have told two different stories, and nobody could fully explain why. Look up at the near side on a clear night and you see dark patches, the Maria, ancient lava plains that give the man in the moon his face. Turn that view around, as China's own Chang'e 4 rover did in 2019, when it became the first spacecraft ever to land on the far side, and the picture changes completely. Rugged highlands stretch for thousands of kilometres. Dark lava plains are almost entirely absent. The crust itself runs measurably thicker than its near-side counterpart, in places by tens of kilometres. Even the chemistry is skewed, with heat-producing elements like thorium concentrated overwhelmingly on the hemisphere facing Earth, as if someone had swept all the moon's radioactive seasoning to one side of the plate. Scientists call this asymmetry the lunar dichotomy, and it has stood as an open question since the Apollo era of the 1970s. It isn't a subtle effect you need specialist instruments to notice. It's visible from a backyard telescope, and it's been staring back at every human who has ever looked up. What wasn't visible until very recently was why. The trouble was always sampling. Every mission that ever brought lunar material home, American or Soviet, landed on the near side, largely because the near side is where a spacecraft can talk directly to Earth without bouncing a signal off a relay satellite first. The far side sat there for half a century, photographed in exhaustive detail from lunar orbit but never sampled, holding whatever answer explained why one hemisphere cooked for billions of years and the other apparently didn't. The South Pole-Aitken Basin was always the obvious place to go looking for that answer. It is enormous, roughly 2,500 kilometres across and about 8 kilometres deep, wide enough to swallow the distance from New York to Los Angeles more than twice over. It is also ancient, dating back to an impact some 4.25 billion years ago, so violent that energy estimates for the collision run into the range of 1 trillion nuclear weapons detonating at once. A crater that size and that old effectively punched straight into the moon's mantle, dredging up material from deep inside the body in a way no smaller, younger basin ever could. If any single site on the moon held the answer to the dichotomy, Planetary geologists had bet on this one for the better part of 2 decades. American planning documents going back to the early 2010s had already flagged South Pole-Aitken as one of the highest priority sampling targets in the entire solar system, precisely because a scar that deep is one of the few places anywhere on the moon where material from far beneath the crust might realistically reach the surface. China simply got there first. Chang'e 6 finally gave scientists a sample pulled directly from it. The basalts are dry. They're stubbornly old and stubbornly young at the same time, and they shouldn't have erupted at all. The first thing the return samples nailed down was a precise timeline. A research team led by Lee Cooley at the Institute of Geology and Geophysics dated 108 individual basalt fragments one by one, using the same lead-based radiometric dating that anchors most of planetary chronology. Of those 108, 107 clustered tightly around a single age, 2,807 million years ago. The lone outlier, a coarser, higher aluminum fragment likely blasted in from elsewhere, came back at 4,203 million years old, more than a billion years older than everything around it. Put those two numbers side by side, and you get a volcanic story spanning at least 1.4 billion years on a single small patch of the far side. Old eruptions, then an enormous gap, then eruptions again far more recently. On its own, a long volcanic history isn't unusual. Near side samples from Apollo and Chang'e 5 had already shown lava reaching the moon's surface from roughly 4 billion years ago down to about 2 billion, with hints of small, isolated eruptions as recent as 120 million years back, almost yesterday in geological terms. What made the 2.8 billion-year-old far-side basalts genuinely strange wasn't their age in isolation. It was that nobody anywhere on either side of the moon had ever dated an eruption from exactly that window before. An independent team analysing fragments from the same sample batch, publishing separately in the journal Science, reached the same age for the young basalts and ran into the same puzzle. Both groups tested the rocks for heat-producing elements and both found them nearly stripped out. Not enough of a heat budget under standard thermal models to explain how magma was still finding its way to the surface 2.8 billion years into the moon's life. The leading explanation on the table right now is architectural rather than chemical. The crust beneath the Apollo Basin sits unusually thin, a scar left over from the original South Pole-Aitken impact itself, and researchers suspect a roof that thin might let small residual pockets of mantle material erupt long after they should have frozen solid anywhere else on the moon. It's a plausible fix for the timeline. It is not yet a confirmed one, and the researchers involved have been careful to frame it as a hypothesis rather than a settled answer. Think of it like a campfire built with almost no fuel that somehow keeps smouldering long after every other fire nearby has gone cold, simply because the ground underneath it happens to be thinner and lets a little residual heat leak through from below. That's the working picture. Whether it's the correct one is still an open question. What was reawakening the moon's magnetic field at almost the exact same moment these long-delayed basalts were forming? Rocks don't just record when they cooled, they can record what the world around them was doing while they hardened. If a rock contains iron-bearing minerals and there's a magnetic field present as it solidifies, those minerals lock in the direction and rough strength of that field, freezing it in place like a compass needle caught mid-swing. Earth's rocks do this constantly, and it's how geologists reconstructed our planet's history of magnetic reversals. The moon did the same thing once, back when it still had an active dynamo, a churning liquid core generating a global magnetic field roughly the way Earth's does today. By the time Apollo astronauts brought near-side rocks home in the 1970s, scientists had already pieced together a rough decline curve for that ancient field. It appeared strong early on, at points comparable in strength to Earth's own modern field, then weakened sharply somewhere around 3.1 billion years ago, and in most reconstructions built from near-side samples alone, seemed to fade gradually toward nothing after that. Strong, then a steep drop, then a long, quiet decline. That was the accepted shape of the story for nearly 50 years. Researchers at the Institute of Geology and Geophysics tested 4 Chang'e 6 basalt fragments for exactly this kind of frozen magnetic signal, marking the first time anyone had paleomagnetic data from the far side at all. What they measured didn't fit the fade to nothing model. Instead of continuing to weaken after 3.1 billion years ago, the field strength recorded in these 2.8 billion year old rocks had actually climbed back up. Not all the way to its early peak, but a real, measurable rebound, arriving in a stretch of lunar history where almost no prior sample had existed to check it at all. One peer reviewer on the paper reportedly called the result highly original, noting that it filled a billion-year gap in the moon's paleomagnetic record that Apollo-era samples had simply never been able to reach. Picture the old graph scientists had been working from. A single curve, rising steeply on the left, peaking early, then dropping and flattening out toward the right. A field going gently to sleep over billions of years. The new far-side data doesn't erase that curve. It adds a small, unexpected bump partway down the slope, a spot where the line should keep falling, but instead ticks back up before presumably resuming its decline later on. A sleeping field that stirred once, for reasons still not fully understood, and then went quiet again. A rebound implies something changed deep inside the moon to reinvigorate a dynamo that was supposedly winding down, whether that's a shift in the core's energy source or some renewed driving force nobody has fully identified yet. The scientists studying the samples have floated both possibilities without settling on either one. What stands out is how precisely this magnetic resurgence lines up with the volcanic episode that, by the numbers, shouldn't have had enough heat to happen. 2 independent lines of evidence pulled from the same handful of far-side dust, both pointing at the exact same suspiciously active moment, 2.8 billion years in the moon's past. The driest place ever measured inside the moon sits buried in the far-side mantle, and it is drier by a wide margin than anywhere scientists had checked before. Water locked inside solid rock doesn't look like water anyone would recognize on sight. It's bound into the crystal structure of minerals, only released when that mineral is melted down in a lab and the resulting glass or grain run through a mass spectrometer. A team led by Hu Sen examined tiny mineral inclusions in Chang'e 6 basalt, apatite crystals and pockets of melt trapped inside larger crystals as they formed, and worked backward mathematically to estimate how much water had originally been present in the mantle source that fed these eruptions. The number that came out was somewhere between 1 and 1.5 micrograms of water per gram of rock. For comparison, 2 decades of near-side sample studies had already shown lunar mantle water varying enormously depending on location, from roughly 1 microgram per gram at the driest known near-side spots up to around 200 at the wettest. The far side result sat at the very bottom edge of that entire known range, the lowest water content ever directly measured from inside the moon. It also marked something else, the first time anyone had measured mantle water specifically from the far side since every earlier number, however low, had come from near-side material only. A separate team, working through the same broader sample set and led by researchers at Nanjing University alongside colleagues at the Chinese Academy of Sciences, found something that sits neatly alongside the dryness. The mantle source feeding these basalts wasn't just low on water, it was geochemically stripped down across the board, described in the published study as ultra-depleted, more thoroughly drained of key elements than any previously known lunar mantle source. 2 competing explanations are currently on the table. Either this particular patch of mantle started out primordially depleted, poor in these elements from the moon's very earliest days, or a massive melt extraction event, plausibly triggered by the same ancient basin-forming impact, pulled those elements out long before Chang'e 6's basalts ever erupted. Researchers connected to the water study have noted that the overall dryness fits reasonably well with the giant impact model of the moon's origin. The long-standing idea that the moon condensed from debris blasted off early Earth by a Mars-sized impactor, an event violent enough to leave the resulting body starved of volatile elements like water right from the start. That's a strange thing to sit with. The far side isn't physically farther from anything. It's still the same small body built from the same original debris disk as the near side. Yet somehow its interior ended up measurably drier than the hemisphere facing us, which means whatever dried it out happened locally, after the moon had already formed, not as some leftover property baked in from birth. Pull the iron and potassium out of a Chang'e 6 basalt and run it through a mass spectrometer. And every road in this story starts leading back to one impact. What comes out of that process is a ratio of isotopes, atoms of the same element carrying slightly different weights depending on how many neutrons sit in the nucleus. Compare that ratio to iron and potassium pulled from Apollo and Chang'e 5 near side samples, and researchers publishing in the Proceedings of the National Academy of Sciences found a consistent, measurable difference between the two hemispheres. The far side basalts run isotopically heavier in both elements than anything ever measured from the near side. Heavier iron isotopes can, in principle, be explained by ordinary magmatic processes, minerals crystallizing and separating out in ways that concentrate certain isotopes over others as magma cools. Potassium is harder to wave away that easily. The potassium signature specifically required a mantle source that was already isotopically heavier to begin with. And the mechanism the researchers point to as most likely is potassium evaporation, with lighter potassium isotopes boiling off preferentially during an event hot and violent enough to vaporize solid rock outright. In the geological history of that region, the South Pole-Aitken impact is essentially the only event extreme enough to have done that. It's the isotopic equivalent of finding scorch marks on a wall and being able to say, from the pattern of the char alone, roughly how hot the fire got and which direction it was blowing. This single data point threads straight through everything found so far. The impact that carved the basin didn't just leave a hole in the ground and walk away. It appears to have cooked off volatile elements locally, reshaping the isotopic and chemical makeup of the mantle sitting directly beneath it. The same mantle that would later feed the 2.8 billion year old eruptions. The same region where the magnetic rebound was recorded. Numerical models built even before Chang'e 6 ever launched had already proposed a mechanism for how one impact could do this at planetary scale. Heat unleashed by a basin-forming collision. This large can drive mantle-wide convection, physically dragging heat-producing, chemically enriched material toward the opposite hemisphere over the following hundreds of millions of years. If something like that happened here, it would help explain not just the far side's dryness and depletion, but why the near side ended up with its lava plains, its concentrated thorium, and its unusually long volcanic history in the first place. One impact, one slow convective shove, and two very different geological futures for two hemispheres of the same small world. It reframes the entire dichotomy as something closer to an aftershock than an original feature of the moon, a hemisphere-scale scar from a single bad day billions of years ago, rather than a difference the moon was simply born with. Which direction did that impact even come from? For years, the accepted answer relied on the Basin's outline: oblique impacts, ones that strike a planetary surface at a shallow angle rather than straight down, tend to leave elongated, slightly teardrop-shaped craters rather than perfect circles, and the long-standing reading of South Pole-Aitken's shape had the original impactor arriving from the south. A team led by Jeffrey Andrews Hanna at the University of Arizona went back and modelled that outline again in 2025 and found the basin actually narrows toward the south rather than the north, a detail that points to an impactor travelling the opposite way, from north to south rather than south to north. That distinction isn't a minor bookkeeping correction. Think of it the way a demolition crew thinks about which way a building falls. Change the angle of the initial charge, and you change where every piece of debris ends up, sometimes by hundreds of meters. Scale that up to a collision that reshaped an entire hemisphere, and the direction the original impactor traveled determines where the resulting ejector and heat pulse would have landed, which matters enormously for any model trying to explain why the near side ended up chemically enriched and the far side ended up stripped bare. Flip the direction of the original impact, and the mantle overturn models built to explain the dichotomy may need to be reworked from the ground up. Nobody studying this is throwing out the impact driven asymmetry idea because of it. But more than 4 billion years after the fact, scientists are still actively arguing over which way the hammer swung, using nothing but the shape of the scar it left behind. There's a smaller, stranger detail sitting alongside all of this that nobody has fully explained either. Chang'e 6 soil behaves differently in the hand than Chang'e 5 soil did. The near side material collected back in 2020 collapses easily under its own weight, the way dry sand does when you try to pile it into a mound. The far side material, by contrast, holds its shape on a steep slope instead of sliding away. Researchers suspect the difference comes down to the shape and surface texture of individual soil grains. But the underlying physical cause remains an open question, one with real, practical consequences for anyone eventually trying to build a lunar habitat out of locally available soil. One robotic scoop, one small patch of one ancient basin, and the story of the moon's two faces has had to be rewritten twice over in under 2 years. A heat budget that doesn't balance. A magnetic field that came back from a decline nobody thought it recovered from. A mantle drier than any other point ever measured on the moon. An isotopic signature tracing straight back to the violence of a single ancient collision, and now a live, ongoing argument over which direction that collision even came from. All of it pulled from 1,935.3 grams of dust, a sample lighter than a bag of sugar, taken from a basin that spans 2,500 kilometres. That basin has barely been touched. Chang'e 6 sampled one corner of it near the northeastern rim of the Apollo Basin, leaving the vast majority of South Pole-Aitken's floor, and almost certainly its oldest and deepest material, completely unexplored. Somewhere in that unsampled ground could be the answer to the heat budget problem, direct evidence of whatever briefly restarted the lunar dynamo, or a mantle sample even drier or stranger than the one already in hand. Nobody knows yet, because nobody has looked. Future missions are already aimed at closing that gap, from further Chang'e sample return flights to NASA's Artemis program, which is targeting the lunar South Pole directly, close enough to the basin's edge to eventually put instruments and eventually people on ground no lander has ever reached. Each of those future missions will be testing the same rough sketch scientists have pieced together so far. A moon shaped by one catastrophic impact, whose consequences apparently rippled through billions of years of volcanic activity, magnetic history, and mantle chemistry, and possibly reshaped an entire hemisphere in the process. For nearly all of human history, the far side of the moon was a shape we could only guess at, hidden forever by the same tidal lock that keeps it permanently turned away from Earth. It has been visible from orbit for barely 60 years and touched, sampled, and carried home for barely one. It has only just started talking, and everything it has said so far has complicated the story of the moon rather than settled it.